Hi, good morning and welcome to the ZP Developer Zone webinar. So every Thursday at 8 a.m. London time, we like to do a webinar for members of our ZP Developer Zone. These members are typically sort of academic startup backgrounds, and we like to do these sort of webinars and answer questions that have essentially come in. So let me just really jump straight into it. So there's a lot to cover today. It's quite a lot in 30 minutes, so I will talk rather fast and I semi apologize for that. Now, first of all, there is something called the ZP Academy. If you're kind of fairly new to electrochemistry and you're not entirely certain with the science, we do have ZP Academy. It has two courses on it that are 100% free, so please check out the ZP Academy. We have the webinars every Thursday at 8 a.m. London time. This is what this is today. We do have collaborations. We have a member of the ZP Developer Zone coming into us this summer. I also want to say hi to Hitcham, who's come online, and I appreciate the people who actually come here quite regularly, and we provide jobs through the ZP Academy, Developer Zone rather. We have a website dedicated to the ZP Developer Zone, and we also host workshops. It's probably worth saying that tomorrow ZP is doing an online workshop where we're going to do some demos and lecturing to a university in India. And so if you're essentially associated with a university and you would like sort of ZP to give an academic or technical presentation on electrochemistry and biosensing along with live demos from our labs, then we're happy to do that. I'm going to go rather fast and sort of jump straight into it a little bit more. So we had a question about glucose oxidase. The quick answer is glucose oxidase is definitely something that we put into our activation solutions. So people who want to make glucose sensors, I think there was some confusion last week whether we put glucose oxidase in there. We do. I'll discuss that. One of our inquirers coming from Indonesia wants to know about making HIV sensors, which I found very interesting because we're going to discuss two infectious diseases today, HIV and malaria. And the key word for HIV is immunosensors. We had another inquirer asking us about screen printed electrodes. They wanted to ask the sort of compare and contrast carbon electrodes, platinum electrodes, graphene electrodes, and then some of our electrodes are flexible, and this is because we're often making them on PET, polyethylene tetraphthalate, or when they're stiff we're making them on ceramic. I prefer in the end PET because everything we do at Zimmer & Peacock, it's with the mind that one day it's going to be on the market and PET is lower cost. And then they were also inquiring about the colors on these screen printed electrodes, and the colors that you often see are the insulator or the dielectric. Some people call them dielectric, some people call them insulators, but that's what the colored materials are. We'll essentially cover that as well. Somebody else, to be fair, had purchased some generation 2 lactate sensors off us, and they simply wanted to know what voltage to apply those, or what voltage to use with those, and I'll discuss that as well. We did have an inquiry about malaria sensors, and I will definitely cover that. It's the same keyword as HIV earlier on. This falls into this category of immunosensors. And then we also had measuring lactate in sweat. I think the questioner has also asked me measuring lactate in blood as well, and we'll cover that. And then we had some questions on oxygen sensing. Right, so that's 7 questions. I've already spoken for 4 minutes, so we have 26 minutes. So we have approximately sort of 3 point something minutes per question. So there was some confusion. Do we or do we not have glucose oxidase in our activation solution? The quick answer is, rather than cause any more confusion, I'll just say there is glucose oxidase in the package when we ship these materials. So we ship these materials so that people can make biosensors of their own. It's probably worth knowing that the surface that you should be using if you're making your own biosensors is platinum. If you're making what we call a generation 1 glucose sensor, and this is what this formulation is for, then you should be using platinum. And the yellow color that you see is the enzyme. So I'm telling you it, and the color itself is actually due to the enzyme. So glucose oxidase has this quite distinct yellow color about it. So I'm going to come off that topic now, because I say, at this point, once the person's received this product, we'll be able to help them a bit more about it, but it does have glucose oxidase in it. Now, this other questioner is coming in about, they want to make HIV electrodes. First of all, I want to just, when I was searching about this HIV and malaria this week, I want to, first of all, I want to cite the reference that I saw this very interesting cartoon online. And it essentially summarizes everything that we say at Zimmer and Peacock. They have an electrode there. They have a antibody on the surface that sort of gives you your recognition. And then they show the way the signal drops like this. And that, to me, tells me that they are, in this paper, I don't need to read the paper to kind of know that they're saying screen-printed electrodes are a good platform for doing infectious diseases. They're using essentially an immunosensor where they're putting a recognition molecule like an antibody onto the surface, and they're often probably running what we call blocking assays, because their signal drops, and it probably drops because when they get specific binding, then the signal changes correspondingly. Now I'm going to flip slightly and go back to the actual question, which is the person wants to make an HIV sensor. So one of the questions in a bit will be, contrast gold and carbon. So once upon a time, when talking about making sensors for infectious diseases, be it HIV or be it malaria, I'd actually talk about use a gold electrode and do a self-assembled monolayer. So a self-assembled monolayer, they often have what's called a thiol group. This is a sulfur atom with a proton in it, SH if you're a chemist, and those bond really well to gold electrodes. I've really gone away from promoting gold electrodes these days for doing immunosensors. I think self-assembled monolayers are not always as stable as you would like, but it's more because the price of gold is actually going very high, and I'm not convinced that the price of gold is really ever going to come back again. I mean, gold is in high demand in many industries, and so I think gold prices will always be high, whereas carbon is much easier to source and is a much more lower cost. So this person is interested in making HIV sensor. I'll get back to the point. In that case, I say it all the time, but it has to be the hypervalue screen printed electrode. I'm going to talk fast because I got people online today like Hitcham who have heard this so many times. I don't want to bore them, let's say, with it. First of all, the paper to start with is this paper. It is free. It talks about making a sensor for HCG. We use this strategy all the time. It's quite straightforward. Take your carbon electrode, drop cast onto it. First of all, we did a cyclovoltammetry on it. If you're not sure about cyclovoltammetry, look at the ZP Academy. We've got 2 free courses there. Look at that. We have something called pyrene NHS. So pyrene is because these aromatic rings will stick really well to the carbon, and this is what's called an NHS group. It's quite reactive, and so we drop cast that onto the electrode, and we get a surface of what's called NHSs, and this will allow us then, and we do cyclovoltammetry at every step. This will allow us then to bind the antibody to that surface. So this person wants to make an HIV sensor. Therefore, they need to recognize what's the macromolecule that's going to give me a specific binding to, HIV, let's say. So they have to identify that. At which point, then they can take the carbon electrode, add a reagent called pyrene NHS. That will give them this surface of NHS moiety, to which then they can bind their antibody that they've chosen, and then they will block the surface in a second step using BSA, bovine serum albumin, or they can use things like chitosan. Now the reason I keep showing these what's called cyclovoltammetry is every time we do a step, we use cyclic voltammetry then to characterize that
And then they
step and make sure that we actually functionalize or change the electrode in the way we thought we were going to do. Now, I'm going to go quick again because Hitcham's seen this before, but we use the way we run in the paper. We talk about differential pulse voltammetry. I'll say it several times, but the methods for reading these kind of sensors are differential pulse voltammetry, square wave voltammetry is pretty good, and I would actually recommend EIS, electrochemical impedance spectroscopy. So we essentially, if there's no antigen or no virus present, you will get one signal. If you then start binding, the signal will change accordingly, and so you should have a signal that's proportional to the analyte of interest. That will basically bring you to a kind of publication level. Now, one of our inquiries this week is much more interested in making a product, so we'll talk also about how to go beyond just publishing a paper. So that will bring you to almost a publication level, but I will cover how to actually get beyond publication level and get closer to an actual product as well. So comments: use square wave voltammetry, use differential pulse voltammetry. I would actually prefer impedance spectroscopy, which does affect that you do have to get a slightly better potentiostat. The inquiry here is in Indonesia. There's a good company there called PT Mab, run by Hasim, and I would actually discuss this with him. And you will need connectors. The connectors that you're looking for, they're for a 7mm wide screen printed electrode, and the banana plugs that you need it for are 3mm. I know it's being very technical or detailed on that, but I apologize for that. But you need a connector for 7mm screen printed electrode, and the banana plug adapters on the back side you need for 3mm banana plugs, and you need the hypervalue carbon electrode. And I will sort of come off the topic now because I have spoken on this topic quite a lot. Now this is another question that came through as well, which was regarding what's the difference between carbon, silver, gold, platinum and graphene. Once upon a time I would say to people there's no real difference between using a carbon electrode, a platinum electrode, a gold electrode. These days I actually tend to bring people towards carbon electrodes just because of the cost. Platinum and gold are really accelerating. Well, not accelerated, but are really increasing in price. Graphene should be intrinsically low cost. The problem with graphene is many graphene electrodes are made by vapor deposition, and it is still quite costly to produce graphene electrodes. I know that there's one company on the web who make a sort of graphene electrode for R&D, and I think it costs something like £20 an electrode. So you've got to be careful with graphene because just of the cost, and it's not the cost of the materials, it's the cost of the process. With silver, gold and platinum, it's actually the cost of the materials that's the problem. Carbon is low cost and actually does work in many of our applications. The only time these days I would suggest you use platinum is if you're making what we call a generation 1 glucose sensor. Any sensor where it uses an enzyme, and the enzyme is often an oxidase, and oxidases therefore produce hydrogen peroxide. Hydrogen peroxide, if you're detecting that on an electrode, platinum is your best choice. Your second best choice is gold, and carbon is horrible for that. If you're going to use carbon for testing, for detect hydrogen peroxide, you have to catalyze the surface with things like nanoparticles or organic mediators. So my choice these days is carbon. I'm sure graphene is good, it's just the cost of production of graphene that's the big issue. And I used to suggest gold for making immunosensors, because with a gold you can make a self-assembled monolayer. From a self-assembled monolayer you could then attach the antibodies. But honestly these days I just say use this strategy I showed earlier on, which is use that pyrene NHS linker and skip the idea of gold, just go straight to carbon. The guy here is asking, some of our materials are flexible and some of them seem stiff. When they're flexible, we're not using paper. I probably will end up using paper eventually because I like the idea of the biocompatibility and the sort of, ability for it to break down in the environment. At the moment we're on PET. In order to kind of overcome that environmental impact part, we are actually allowing people to send used screen printed electrodes back to us. We have a recycling scheme. And for that then we'll give them a license to Julie for free for a month. So I am aware of the environmental issues associated with shipping these screen printed electrodes. We are actually accepting them back and rewarding people for sending them back to us. At the moment we're not on paper, we're either on PET, whose trade name used to be Mylar, or we're on ceramic. The green or blue layers that you see are insulator. It's necessary because, I'll maybe go to the next slide. The reason that we have these green or blue layers is because otherwise the conducting track, so this point on the back side of the electrode we will have where we make the electrical contact, and then we have a conducting track, and then we have an exposed area here on the sensing end. We want to very much define the working electrode. In electrochemistry, the signal is often proportional to electrode area. So we want to very much define it, and we define it by actually putting insulator everywhere and only sort of exposing one part of the track, which we then refer to the working electrode. Otherwise, somebody could put their sample on there, and depending on how it spreads across the screen printed electrode, it could cover more or less electrode. So we want to make sure that one of the parameters is not variable, and that's the exposed working electrode area, because signal is proportional to area, and so we reduce the variability by having the insulator there, so that even if liquid gets on top of the insulator, it's not making contact with the underlying conducting track, and therefore not giving us extra signal. So we use insulator to make sure that the exposed electrode is very defined. If you didn't have it, then somebody could put a drop onto the electrode. It could spread around, and depending on how much it spreads, you would be covering more or less electrode, and therefore your signal would be proportional to, in part, to that coverage, and it would make for a very confusing signal to interpret, because signal should be proportional to concentration. But if it's proportional to wetted area, then your signal could be higher or lower, not due to concentration, but due to wetted area. One thing I want to cover here is the only graphene electrode on the market that is fairly competitive is one that we make, and it's probably just worth checking out that URL if you're particularly interested in graphene electrodes. We are doing a graphene electrode an order of magnitude less costly than other electrodes on the market. I'm just not absolutely convinced that graphene is necessarily better than graphite. You have to understand that one of the motivations in academia is people need to invent and publish new work, and so graphene is new material, and it allows people therefore to do innovation upon it. But it doesn't mean it necessarily adds real value to the actual sensing of, let's call it, malaria or HIV itself. But if you want to practice with graphene, we do have some screen printed graphene electrodes. You have to look at the link and the video, because you'll see with our graphene electrodes, they're quite silvery. And if you buy graphene electrodes and they're not silvery, it tells you really that there's not graphene there, it's just graphite. So just make sure that you watch the video and you get a sense of the difference between graphene and graphite, because I have seen graphene electrodes that look very dark black and very matte, and it without any shininess or silveriness to them, and it sort of tells me that really they're the claim is it's graphene, but actually it's just graphite. Alright, I've said enough about that. We have had somebody buy some of these generation 2 lactate sensors. Earlier on I did use the word generation 1 glucose sensors, and I talked about glucose oxidase producing hydrogen peroxide, and then you detect hydrogen peroxide directly. That's a generation 1 glucose sensor. These people have purchased a generation 2 lactate sensor, and they just wanted to know what the voltage they should apply is. And the quick answer is it's 0 volts. And this is probably even one of the sensors that we've shipped to them. And so what you can see here is we have this called the break-in time. This is the time when the sensor's kind of finding its equilibrium. And then the scientist has tested it at 1 millimolar, 2, 3, 4, 5, 6, and 7. They have really nice, we call this a staircase. And the voltage that they've used to gather this data is 0 volts. So that's the kind of signal, and the signal you'll get and the voltage you should use when using a generation 2 lactate sensor. I suspect we'll get some questions about what's the difference between generation 1 and generation 2. If those questions come in, we'll answer it pretty soon. We have something called the application zone on our website, under knowledge base application zone. There's lots of videos there about us testing biosensors. If you're interested in biosensors or how to test biosensors, it's probably worth going through those videos. There's at least 9 of them up there, and it's probably worth watching them all just to get a sense of how we do this kind of lab work. Question 5, malaria. So I thought, first of all, I just did a quick bit of research on this. Now, I think the value that people can bring to infectious diseases is to actually identify the biomarker that's indicative of the disease. And if they understand the biomarker, then they can identify the macromolecule that's will bind or is indicative of that biomarker. Now, in this particular paper, the things that I noticed were, that in fact, they are using exactly the same immunosensor strategy that I was talking about earlier on. And I also noticed that they were doing exactly what we were talking about, which was as they were layering on the materials onto this electrode, the signal, they were measuring it by cyclovoltammetry, and the signal was changing with each layer. So it tells me they're basically doing the same that what we tell people to do at Zimmer and Peacock, which is, reassuring. And then they actually finally measured it using impedance spectroscopy. So, earlier on, I was saying, if you want to measure HIV, take a carbon electrode, take one of those hypervalue carbon electrodes because they are so low cost, use the pyrene NHS linker, bind the antibody to that. You can follow each step using cyclovoltammetry, and I recommended impedance spectroscopy to actually read the final assay. And it's exactly what they did in this paper. They have used things like gold nanoparticles. There's nothing special about gold nanoparticles for me. They just increase the surface area to give you a higher signal density. But I would actually, to the people who are reaching out to us regarding how to make a malaria sensor, or how we would do it, we would follow the principles in papers like this, but we would not use the gold. As I say, the gold price has gone, is going very high, and I think gold is an in-demand material. I really don't see it coming back down in price, so I would actually recommend something like the hypervalue carbon electrodes. And actually we can interpret this kind of data. What they have here is, I don't want to get all geeky on people at the moment, this is what's called the Nyquist plot. Basically, the spectrum is changing with the more, in this case, the more cells. They were looking at the red blood cells that were actually affected by the malaria parasite, and they had a signal that changed proportionally, and they essentially plotted out signal versus concentration in the graph next to it. Now, that seems very academic because it just leaves you with basically scientific data. The way we would actually approach this, for example, is we would take one of our hypervalue carbon electrodes, we would functionalize it to be specific to essentially the disease. We would have to get some advice on, what's the biomarker for malaria. But if we understood that, then the way these kind of assays work is you take a sample, you put it on the sensor. Now we have a very powerful workflow. We call it the ZP accelerator. So we take the carbon electrodes that we have, we functionalize them. We use a set of electronics that we have at Zimmer and Peacock. Now what we do is we would look for a sample, whether it had HIV in it or it was a sample from a malaria patient, and we would want to analyze it on a third-party device. So here's HIV. Maybe the gold standard is PCR. If it's malaria, there might be an ELISA assay, but we would want to take a real biological sample and test it the way that is considered the gold standard today. But then we'd want to take the same sample and actually test it on the now developed biosensor. Because what we would do is we would test the real sample on a biosensor, and we would actually immediately send the data using an app. So this is a workflow that we have. We send it to a cloud database that we have called Julie. So we end up moving the raw electrochemical data to the cloud, and so we're able to sort of see a signal versus concentration in our cloud. And what we're also then asking is, what was the result from the gold standard? Because in the end, you want to get, in order to be able to claim good accuracy, you need to be as close to the gold standard as possible, whether that gold standard is an ELISA assay or whether it's a PCR assay. The reason I say all that is because what we want to do then is keep on doing the data science until we get a good correlation between the new sensor, which is obviously really a point of care device, versus the reference value. And Julie, our database, allows us to keep on analyzing the signal, iterating, until actually the correlation is as strong as we think we can get with the data set that we have. So the reason I bring this up is because at ZP we support academia. So we had the inquiry about HIV today, and so I've shown you a way of getting essentially to a sort of scientific paper level, but then there's a level beyond that, which is we need to test real samples and start making a product from it. And so our ZP Accelerator platform is that next stage, because where the academic work will leave you at a sort of sensor that works in the lab, what we want to do then is actually take those sensors and start testing them with real samples. Once upon a time, people would spend years before they actually started testing with real samples, but that's not our strategy. We actually start testing real samples very early. And the only thing we need in order to do that and be quick about it is we need to be able to test that sample twice. Once on the biosensor, and also once by what's considered by the clinicians as the golden standard. And then we can compare our accuracy versus what the truth is of the gold standard. And that's a workflow that we call ZP Accelerator. Right. I'm going to go a little bit quicker now. Somebody wanted to know about, they wanted 100 lactate sensors. We said, these are on the website. If you want to test these lactate sensors, for example, in blood, you literally just need to get something like 30 microliters of blood and just pop it on the end of the sensor and cover up these electrodes. I've done it myself. A drop of blood is more than 30 microliters. I have done this, and so you can cover that with a drop of blood and test blood. With sweat, you probably need a sweat patch, and we do have such technology on our website as well. In the end, the quick answer to is it doesn't matter what liquid you're trying to test, you just need to cover the end of it, and then the enzymes in that the enzymes on the sensor will start reacting with the analyte of interest, and then we will electrochemically be able to follow that reaction. Now with blood, you have some background signal. With sweat, you'll have a different background signal, so you have to kind of essentially do the work in order to understand the extra signals that these complex matrices bring to you. And I would also recommend, I called something called the knowledge base earlier on, that's on the ZP website. It's probably worth watching those videos as well. Now I can see it's 8:28 here. So final question. Question came in and said, hi, I'm working on a research project and have some questions. The questions seem to be around oxygen sensing. I'm going to talk quite quickly. Oxygen sensors were developed originally in 1956 by a guy called Leyland Clark. And I don't think oxygen sensors have actually moved on that much since 1956, apart from what ZP is doing. So when you look at Leyland Clark's oxygen sensors, these are some of them that are on the market today. They look a lot like lab pH sensors, and it's because the construction of these traditional oxygen sensors is very similar to a pH sensor. What's happening is that you will have a reference electrode and a working electrode. The working electrode is platinum. Oxygen comes through a diffusion layer, reaches the platinum electrode, where they're basically reducing by electrochemistry oxygen to water. And on the previous slide I didn't emphasize it, but a lot of these commercial electrodes are using about minus 630 millivolts to reduce oxygen down to water. So the keywords here are Leyland Clark, or the key statements are Leyland Clark invented this in 1956. I would categorize this as an amperometric oxygen sensor. The modality of detection is the reduction of oxygen to water. This is some data of a ZP oxygen sensor. So the magnitude of the signal is what's important. So we have a magnitude here of 4 microamps. We deoxygenate the solution and the signal drops closer to 0. So we kind of go from saturation to depleted oxygen, and the signal changes accordingly. This is exactly the same modality that Leyland Clark electrodes were working. The only difference is the ZP oxygen sensors are a fraction of the price of those large electrodes, and they're really solid state. These are much more akin to a glucose sensor, and it's probably worth saying again that on the ZP website under the knowledge base we'll actually have videos of us testing oxygen sensors. Just a bit of a warning, I have noticed recently there's been a bit of a spike in people's, you can buy screen printed electrodes in the USA and Europe. The price controls are quite good, but I am noticing that in some countries people are really starting to charge quite a lot of money for the potentiostats and the screen printed electrodes. So I just want to say be careful of the pricing that's going on at the moment. So we are shipping something like 500 screen printed electrodes and a USB potentiostat and 12 months license to Julie. That price is much, the whole package is much lower than people are actually selling just the potentiostats at. So just be really careful out there, depending on where you are globally. So similar for the, there's a very popular palm sense potentiostat. You be careful wherever you are, if you're in the UK or Europe or USA. We're shipping that potentiostat plus 200 screen printed electrodes plus the Julie license, at a price that's lower than anyone else is actually selling the potentiostat at. So just be careful. That's what I want to say. Right. In summary, we are definitely using glucose oxidase in our activation solutions. I have no worries there. With the HIV, use the hypervalue carbon electrodes, follow that HCG paper that we indicated. You'll probably end up having to use impedance spectroscopy, and because you're in Indonesia, talk to PT Mab, they're a good company. In the end, if somebody asked me, knowing nothing else, what would you recommend as a screen printed electrode, then I would say our hypervalue carbon electrodes, because we produce it in the at a very high volume, so we achieve good quality and low price, and actually we can make it work for most things. The generation 2 lactate sensor, you have to use it at 0 volts. For malaria, there is good literature precedence that you can do electrochemical detection of malaria. My recommendation is, if you were to do it yourselves, I would use the HCG strategy, and I would say don't feel like it just stops at a laboratory experiment. At least at Zimmer and Peacock we know how to take it onto real samples, and from real samples then, once you've got data on real samples, then your sort of valuation can go a lot higher on that. Measuring lactate in sweat, whether you're measuring lactate in sweat or measuring lactate in blood, you literally just need to cover the working counter and reference electrode, and a volume of about 30 microliters is enough to do that. The sensors don't care whether it's blood or sweat. They literally dumb, they don't know. Questions on oxygen sensing. The key words are Zimmer Peacock does have some webinars about oxygen sensors, but in the end, people are using platinum working electrodes at a voltage of about minus 630 millivolts. The designs haven't changed so much since 1956, and the only solid state low cost oxygen sensor that I think is out there is obviously what we have at Zimmer Peacock. Alright, it's 8:34. Thanks Hitcham for your attention today. Hopefully see you soon enough. And yeah, unfortunately I have some meetings to go to, but thank you for your attention today. Okay, take care. Bye bye.